All right, so moving into chapter 6, we're still working on quadratics. So 6.1 is quadratic functions. Okay, we're going to start with them in the form f of x equals that ax squared plus bx plus c. We're going to plot some points. Okay, that's probably what we're going to get to today, is plotting some points. Then we're going to graph quadratic functions of the form of f of x equals ax squared plus c by transforming the parent function, which is f of x equals x squared. Okay, so if we look at this, what's the difference between this parent function and the function here? What's the difference between this one and this one? All right, so the c and the a are different, and so we're going to learn in this section how c and a affect the graph. Okay, because they make changes to it. They're going to move it up and down or left and right. They're going to make it skinnier or fatter. Okay, they're going to do some different things, and we're going to learn about that. And then 3, we're going to determine the vertex, domain, range, and axis of symmetry of a quadratic function of the form f of x equals ax squared plus c. I promise it's not as terrible as it sounds to start with. It is just section 1. All right, so let's look. Here we have a comparison between an equation and a function, and linear and a quadratic. Okay, so it's kind of cool to look at. An equation only has one variable. All right, so we have like 2x plus 3 equals 7 is linear. 3x squared minus 5x plus 8 equals 0 is quadratic. What's the difference between the linear and the quadratic equation?
It has like it's the not coefficient, the squared values and stuff.
Okay, the squared values. Okay, so they each have one variable, except this one, okay, this one has an x squared and this one has an x, right, in the quadratic. So in a linear, the highest we'll have is an x, and that's linear. If we ever have an x squared value, it is going to be, if x squared is our highest, it's a quadratic. Okay, linear is a line when we graph it. A quadratic is a parabola when we graph it. Okay, so I'll put those up there too. All right, so an equation is going to have at most one solution if it's linear. If it's quadratic, it's going to have at most 2 real number solutions. Versus a function, when we use the function form, okay, we have 2 variables in a function. So this is, because this f of x, what is, a lot of times we call this the y value in that input-output. Okay, so in this case, we can put one number in and we're going to get another number out. So we have an infinite number of ordered pair solutions that can form the line. All right, and with our quadratic, we have an infinite number of ordered pair solutions, only this time they form that curve or that parabola.
F of x is basically just y. Why don't we just put y?
That's a good question, because it's a function. Like they are functions, and that's kind of the issue. Is early on you learned, like, because you were graphing, the focus was on graphing in the coordinate plane. So we learned like y equals 3x plus 2. And so when we solve them, we got an ordered pair. If we put a number in for x, we could get out its y coordinate, right? So, but we could put in any number for x. We could put in 5 numbers, we could put in 12 numbers, we could put in 1,000 numbers. Okay, just how much time do we want to put into graphing it? So the focus was on graphing and having an x and y. Now that you know how to graph, there's like it's stepping up to saying like, well, this is actually a function. It's always really been a function before, but your mind wasn't ready to grasp that idea. Instead of having, because I mean, you know, if we had had a plane that was like x and f of x, well, then that might have made more sense. But that's not how our Cartesian plane looks. But f of x and y are the same thing. You're right. Yeah, we're starting to actually call it by its real name now. We're starting to call it an equation or a function instead of an equation. Because sometimes, like when you're reading the Bible, right? You read one scripture to, 2 years ago and you interpret it and then you're like, oh, this applies to my life in this way. You go back and you read that scripture today and you might be like, oh, I didn't see that before. Oh, yeah. Like math is the same way. Like we build on what we know. Like the more we do math, the different ways in which we see it. Like we notice different patterns or how different numbers evolve. It's the same way when we read our Bibles, right? Like the more we read our Bibles, the more we see and the more connections we make. If that helps. Okay. So let's look down at a quadratic function. So we've got our formula for quadratic function. So f of x, like you said, is our y term. It's the same thing. Then we have a quadratic term because it's the one with the x squared. Our linear term, okay, is the one with just the x in it. And then we have our c, which is the constant. Okay, it's just the number.
You just said in this video that 4 times 3 was 6.
I make mistakes. Okay, then to graph, which is what we're going to work on. We're going to evaluate the values until a pattern emerges from the plotted ordered pairs. Then we're going to draw a curve that connects the points. All right, so number one, I've done all the work except for the graphing. Okay, but so the first one was to evaluate the functions over several values of the domain. So we picked -4. I plugged -4 in. If you look at that, -4, and notice my -4 is in my parentheses because I'm squaring -4. So -4 squared plus 2 times -4 minus the 3. I got 16 minus 8 minus 3 is 5. If you look down through there, do you have any questions about how I put the numbers in?
Are you just putting in any of the numbers just to see like where you have to graph it?
Yep. I just put in any numbers to see where I would graph it. So here I would graph -4, 5. But I was looking for a pattern. And so if I look, I've got 5, 0, -3, -4, -3, 0. Ooh, see? Like, see this one repeats, and this one repeats, and then those repeat. So here is like my middle of that curve. So I can envision my curve there. So you're just plugging in points until you can find a pattern. Mine worked out perfectly, but I have a lot more skills. / it was in the book and I just used theirs. I have a lot more practice than you guys do. Okay, but then let's talk about the graphing part. Because if we can put it into the formula, then we'll be okay with getting the numbers. The graphing sometimes people get confused about. So my first point I'm going to graph is -4, 5. So 1, 2, 3, 4, 1, 2, 3, 4, 5. And then -3, 0. So 1, 2, 3, 0. -2, right? And my answer to that one is -3. So -2, 1, 2. Oh, wait, hold on. Well, I didn't get -3, 0 in there either. I did -2, 0. So -1, 2, 3, 0. Okay, -2, -3, 1, 2, 3. And then I've got -1, -4. 1, 2, 3, 4. And then 0, -3. And then 1, 0. And 2, 5. So 2, 1, 2, 3, 4, 5. Okay, what do you notice? It makes the parabola thing. Okay, so I'm going to draw my curves. Yeah. We want it to be a smooth curve, not a harsh V, but yes. Do you notice anything else?
They're equal on each side.
They're equal on each side. They're equal distant? From what? Like not from the y-axis.
No, but like there's like the same height is also what I meant.
Okay, so there's the same height across here.
Yeah.
So these are the same height.
Yeah.
They're the same height. These are the same height. What about this idea like equal distance? Like could I take this parabola and like fold it in half? It's symmetrical? Okay, where would it be symmetrical? At what point?
Negative 1, 0.
The bottom point, like here?
Yeah, -1, 0.
Okay, if I drew a line up through the middle of that on -1, yeah, that would be my line of symmetry. So since it's a vertical line, what would we call this? Okay, good. What would be the equation for this line of symmetry? Not 0, because it's not on 0.
-1, 0.
Well, -1, 0 is an ordered pair.
Yeah. So it'd be.
Is it one of those inequality things?
It's not an inequality.
It's -1, but there's some sign on it that makes it say, oh, it's a.
It is -1. Good.
Um,
What value is -1? My x or my y?
it's X.
That is, your line of symmetry would be x equals -1. Yeah, because I could fold it in half. And that is going to be very important for us to realize that we can take, if it's a true parabola, if we graphed it correctly, we should be able to fold it in half and find that line of symmetry. Okay? All right, so let's flip over to the other side. Where it says axis of symmetry or line of symmetry. You're going to see it as both ways in your textbook. Okay? Divides a parabola into two mirror image halves, which you guys just did. The vertex is the intersection of the x-axis and the parabola. That's what you guys used earlier. You said like, oh, well, it's down here was that -1, -4. You told me to draw the line there. That's the vertex, okay, where your axis of symmetry and your parabola intersect. Now, this point can either be the place of the minimum or the place of the maximum. This one, right, if my graph opens up, this is the lowest point on my graph. So would I call this the minimum or the maximum? The minimum. Okay, fantastic. If my graph was like this, here's my vertex. Here's my vertex, my line of symmetry. Would this be the minimum or the maximum? Maximum, because my parabola is opening down. That's the highest point on my graph. So your vertex you will often see called as the minimum or the maximum, or the min or the max. Okay, awesome. So this one is the exact same graph we just had. All right, so our axis of symmetry, you already told me, was x equals -1. You already told me my vertex was -1, -4. So then the y-intercept. What has the y-intercept always been?
Y equals mx plus b.
Okay, that's slope-intercept form.
Yeah.
But what was the y-intercept?
The y.
Where it crosses the y-axis. Okay, so it's the same thing. Where does this parabola cross your y-axis?
-3.
Okay, so at 0, -3. That is the y-intercept. Good.
What do you mean 0, -3?
Yes, is that not what I said?
Yeah. He's asking what do you mean because she's saying 0 for the x value because it's on the y-axis.
Oh,
So to
yeah.
graph it, it's 0, -3.
That answer, okay, fantastic. So yes, our y-intercept is always the same. Okay, or it's the same as what it was when we talked about y-intercept with slope, okay, in linear equations. All right, so domain. What's the domain say it is? Okay, domain is my x values or my y values? X values, good. Okay, so why is the domain all real numbers?
Because it's going to continue going out of
It's gonna
infinity.
keep,
If you keep looking, it's going to eventually hit whatever number you want.
right. So check this out. Parabolas either open up or they open down. So the domain will always be all real numbers. Always. Okay, we'll let that go. Wait, how? Okay, Brandon, can you re-explain that again? Why it's all real numbers?
So the domain is just saying like any x value. So because like this goes up and goes out like that, if you said you wanted your x value to be 5,000, and you zoomed this out enough, this would continue going like forever. So if you zoomed out enough, it would eventually hit 5,000.
Yeah, but like if I say I want my x to be 0, it doesn't hit 0.
Yeah, it does.
No.
Right there. Because that's inside the parabola.
Oh, so it's not just the line.
It's not just the
line and
lines.
everything inside of it.
Well,
Correct.
but if you're saying your x value here is 0, it hits 0 is at -3. Your line, if you put an x into this equation, or this function, you're going to get 0, 3. Any of these x values you're going to have, it's not like you're not getting 0, 0, but you will have a point on there.
So whatever number of x I choose,
Mm-hmm.
The line will hit it.
there'll be a
The curve will touch it somewhere.
Basically, you can think of it as, so the place where the x is going to equal 0 is on the y-axis. So at some point, no matter how far to the right or left it is put at, if it's continuously going like that forever, it's eventually going to hit the y-axis, where the x value would be 0 and the y value would be whatever the y value is, however high it is.
Yes, Lauren.
What if it was
If you see it that way.
my mom got me an appointment?
Yeah.
Okay, so it doesn't actually have to be on
The x-axis. Correct.
It's on the y-axis, technically, is where 0 would be at. Because it's showing
But
the value of x is 0. Does that make sense?
Okay, so if whatever number this is, if I want this to be my number and it's coming out to here,
Mhm.
that would still work because it's up here.
Yep.
Okay.
Yep. So you're plugging in your x and you're trying to find your y. You got it. Okay. Now, your range is where it's going to get sticky. Okay? Because your range is your y value. So it's always going to have, we're always going to use this set notation. Okay? Remember this?
Such that y.
Right. So our y value such that our y is greater than or equal to -4. We'll check it.
Greater than or equal to?
I read it as z. Yeah.
Oh, gotcha.
Z.
I'm sorry. It is greater than or equal to. Good call. But if we go back to this graph, okay, I probably should have left that. All right. So you said this vertex, right, was our minimum. So all the numbers have to be above it. So they all have to be greater than or equal to the -4.
Oh, that's easy.
And if we had the other one, like I erased it and I was like, oh, I shouldn't have done that. And say this point was 3, 7. Okay, so our domain, or our range here,
Would be y such that y is less than or equal to 7.
okay, so it's going to be y such that y is, okay, so all of our numbers now are below, so they're going to be less than or equal to 7. That's it. So like your vertex, your minimum, your maximum, your range, all of those things come from the same point on your parabola. So if you can find your vertex, you can find the minimum, you can find the maximum, you can find your range. All of that stuff. And your axis of symmetry, because our axis of symmetry revolves around that. So your vertex is super, super important in a parabola. Okay, and so that's why we're going to get to where we can convert our function from the ax squared plus bx plus c into what's called a vertex form. Okay, because the vertex is super important. Everything in a parabola revolves around the vertex.
What if it's not symmetrical?
Then you've put your numbers in wrong for your calculations.
It will always be symmetrical.
It will always have an axis of symmetry. If it doesn't, you either haven't put enough numbers in to find the axis of symmetry, or you made your calculations wrong. It's kind of a nice self-check.
So it will always work. There'll never be one where it's like the numbers just simply don't work.
Never. A quadratic is a parabola. Just like when we did linear equations, if you got anything but a line, you did it wrong. Okay? Because we're not into hyperboles or hyperbola and different things like that, yet, where they get funky looking shapes. We're not there. We're just taking one step higher than the linear equation into the quadratic. It will always be a parabola. Like I said, so kind of self-checking. So let's see about, actually, let's, what was I going to say? What time do we have? 30. Let's stop there, and I'll give you an assignment.